Hello and welcome to this talk. My name is Leonardo Laguna Ruiz and we're going to talk about modeling analog synthesizers. But before we start, this is a little bit of information about me. During the day, I work as software developer in the system modeler team, but during the night, I am the jack of all trades at my own project, which is called Vult, where I develop software and hardware for music technologies. And one of the things that I enjoy the most is modeling vintage analog synthesizers, specifically the electric circuits that you can find in them. And why do we bother modeling all this old analog equipment? Well, you may have heard people saying that the sound of vinyl record players is much better than MP3 player. And that is true and not true at the same time. So the thing with the analog synthesizers is that they produce a sound that can be perceived as warm and rich. It's more appealing compared to the early digital synthesizers that were producing sound that was perceived as cold and lifeless. And the secret here it lies in the imperfections of the analog synthesizer. Digital synthesizers use some kind of computing element. It can be, for example, a microprocessor, and this microprocessor has a near perfect arithmetic. So every multiplication, every addition has a very good precision. On the other hand, an analog synthesizer is made with components that have imperfections, and these imperfections accumulate. They use, for example, semiconductors, which are non-linear components, and these components saturate, and they also have variability. Not every resistor has exactly the same value. Here we have an example of a digital oscillator that produces a saw wave. You can see how it nice it looks. And if we compare this saw wave against an analog oscillator, you can see how different it is. Even when we are aiming to have a saw wave, it is not a saw wave. It's slightly different. And this difference is part of what makes it appealing. And a big part of what I do is trying to create the simulation models that replicate these imperfections. Going back to the vinyl record player, we could make a regular CD player sound as appealing as a vinyl record player if we add the required signal processing in order to match the sonic characteristics. And how do we start modeling analog synthesizers? First, let's take a quick look on how they are architected. So a typical analog synthesizer is composed by different blocks or modules. They can be oscillators, filters, amplifiers, and other modulators. So basically, you can think about them as being analog computers. And these analog computers perform additions, multiplications, comparisons, integration, and we can say that they even perform trigonometric operations. Here I have two pictures of two different systems. This one, you can see that it has a panel where the different modules are laid out. So we have oscillators, filters, etc. We have a keyboard, and then we have this section that allows us to change the internal connections of the components. On the right hand side, we have a fully modular synthesizer, and you can see that it's composed by different blocks, and each of these blocks is independent and can be replaced, and you have all the controls, but you can also connect in any way you want each of these modules. You have jacks, and you can use wires to create the structure that you want. The synthesizers can be a bit expensive, especially the modular ones, where you get every module separated, and the cost of a module could be in the range of $60 to $1,000. And they can also be a bit bulky and heavy because you have to put them inside a case, so they are not very practical to travel with them. One way that we can overcome these problems is by using a virtual synthesizer. For example, VCV Rack, which is a software that is free and open source, and it tries to simulate the experience of using a modular synthesizer. Here you can see some of the modules that I make, which are real modules, and the equivalents in the VCV rack world. In the virtual synthesizer world, you can have as many as you want, and the cost is not a problem. But you are also losing a bit, which will be the interaction. In a real synthesizer, you can touch all the controls and perform with them, while in a virtual synthesizer you are a little bit constrained because you need to use the mouse, or you have to use a controller in order to help you move the components. Now I'm going to give you a quick demo on how to create a sound using a modular synthesizer. This is the VCV rack interface, and I have already placed a few modules, and I'm going to create a sound using a technique called subtractive synthesis. So I'm going to start with an oscillator that sounds like this. I'm going to change it to a saw wave. And as you can hear, it's a sound that has a lot of harmonics. And next, we're going to pass this oscillator through a filter. And you can hear how the filter shapes the sound. I'm going to take this model that I made, which is it's a mechanical model. It's not an electrical, but it simulates a chaotic pendulum system. We're going to use it to provide some modulations to our oscillator. Now we have a sound that varies over time. Is not a static sound. And next thing that I'm going to do is taking this output, and we're introducing it into an envelope generator, which is gonna allow us to trigger the sound. And now we have a sound that has its amplitude modulated. You can make it longer, shorter, with a softer entrance. And we can add, we can modulate as well the filter. And now let's take a look at the process I use to create the simulation models behind these modules. I usually start my analysis with the schematic, like in this case, this is a filter. And I start by identifying the different blocks and components. And at the same time, I'm developing a board that I use for actually making measurements, like this one. Sometimes I simply make the circuit into a breadboard. Once I have identified all the components, I start making the model in System Modeler. System Modeler provides a wide variety of components that can be used. In my case, could be electrical components, for example, resistors, capacitors, etc. But one of the things that I really like about using System Modeler is that I can create my own components. It is often the case in other simulators that a component is not provided and there is no easy way of integrating it or creating it, or sometimes the way that you create the components it's kind of convoluted. Over the years, I have created a library of components. I have a small version here, and you can see that I have typical components: resistors, capacitors, variable resistors, and operational amplifiers. And these are the components that I use to create the circuits. Now let's start analyzing a simple circuit. In this case, we're going to see the silent key filter topology. We're going to focus on the low pass configuration, and this is the circuit. You can see that it uses 2 resistors and 2 capacitors, and it has an operational amplifier which is connected as a buffer. And from these equations we can see that in order to define the cutoff frequency, we need to either change the resistors or the capacitors, and if we make the 2 resistors the same value and the 2 capacitors, this gets simplified, and we can simply use a pair of variable resistors in order to define the cutoff. In System Modeler, I have already connected all the components into the silent key filter configuration. You can see 2 resistors, 2 capacitors, and 1 buffer. But these resistors are one of my models, which are variable resistors, and both are controlled by this input signal P. The audio is provided with this input signal U, and then is converted into voltage. And at the output, I have a sensor which is going to measure the filtered voltage and provide it in the output V. Now I'm going to test this filter. I have prepared a model here, which this is my filter model, the one that I described before. I'm using a component from the Modelica library, which produces a pulse wave, and then I'm using a saw wave, which is slower, that I'm going to use to change the cutoff frequency of the filter. The output is going to be sent into this model that is going to record the results, and is going to generate an audio file that we can listen to. We can see that simulating a model like this one can take quite some time, in this case 25 seconds, and that is because by using the audio recorder we are forcing the simulator to take 44.1 kilosamples per second. If we remove the recorder, the simulator will be able of going much faster. But one of the nice things of doing this is that we can listen directly to the audio results. Now let's see how we can extract the equations of this simple filter model and create a model that can run in real time. Since I have packed my filter model into a single component, it will be much easier to extract the equations used only into this component. But before doing that, let's check one nice feature. What I did was simulating only the filter component. Since it doesn't have any input, it will not produce any signal. But the nice thing is that we can go to the tools and use the equation browser in Simulation Center. Without going into too many details, what we can see it's a matrix that has one diagonal, and in all the colors of these small boxes are green. What this means is that all the equations are easily solved one after the other. Just to have a reference, let's take a look at a more complicated filter like this one. We can see that in this case we have non-linear blocks, the ones that are orange, and they are quite big. And we also have some linear blocks. So what this means is that it is going to be a little bit more difficult to create this model, since we will have to run a nonlinear solver in order to solve the equations, and that can be very expensive in real time. Just keep that in mind. The model that we're analyzing now, it's linear and it's going to be easy to do. In order to retrieve the equations, we're going to use a system model to get into information about the filter component. Now that we have the model, we can get the equations. You can see that I use the method elimination all, and what this is going to do is going to remove automatically most of the simple equations, leaving us with equations that actually do some computation. Now we can simplify even further these equations by using the command eliminate. And one thing that we want to do is to eliminate the currents. Since the currents do not provide us any extra information, we can just get rid of those. Okay, I think that I have got rid of all the currents. And we can also get rid of voltage calculations we don't care. For example, we don't care about the voltage in the resistors. At this point, we only have the voltages in the capacitors, the inputs, and the outputs. And I'm going to do some replacements in order to compact the equations even more. Now I'm representing the derivatives as dw1 and dw2. And since this system is quite simple, we can represent it as an ODE. And these are the ODE equations. We're going to prototype our implementation of the filter using VCV-Rack and a special module called the VCV-Rack prototype that will allow us to use the Vult language, which is a very simple language that I developed in order to express DSP algorithms. And here we are going to start writing the code. But first I'm going to copy the differential equations that we got and paste them directly in our code. Once that we have calculated the derivatives, I'm going to use an integration method in order to simulate these differential equations. In this case, I'm going to use the Euler method because it's simple and it will be good enough for this example. If you remember, the parameter P represents the position of the potentiometer. It will directly control the cutoff frequency. H, in this case, is going to represent the simulation time step. Finally, I called the filter function and I provide the P and H, which H is the inverse of the sample rate. And in the parameter P, I use an exponential function in relation to the graphical position of the knob. This will help us to make a transition in a musical way rather than linear. If everything is fine, I just need to save this file and we will be able of using it inside VCV-Rack. And here is the code running in VCV-Rack. Let me raise the volume a little bit. To summarize this talk, we saw why analog sounds are perceived as more pleasant, and we also saw that it is possible to capture that imperfection of the sound of the analog electronics into models. I also show you how I use Wolfram language and system modeler in order to make my modeling process much simpler. I can capture very large schematics and analyze them using Wolfram language and system modeler. When making this kind of models, it is very important to note that they need to be very efficient and run in real time. And when you have nonlinearities, the analysis can get quite complicated. And the biggest reward for me is listening to the music that the people make with my models. And to close this presentation, I'm going to leave you with an example that my friend Omri Cohen made.
Hi, I'm Omri. I'm a musician based in Germany, and my instrument is the modular synthesizer in two forms, hardware and virtual. The virtual part is coming from VCV-Rack, a free and open source virtual modular synthesizer that is based on the Eurorack format, just like I have here. For me, using a modular synthesizer is all about the interaction with the instrument, live acting and reacting to the sounds. I have a small patch ready. I will go through the modules and devices I'm using. The most important module here is the ES9, which is basically a DC coupled audio interface that allows me to send audio and control voltage from and to VCV-Rack, and by that connect both worlds, virtual and analog. I have here the first voice coming from an oscillator, going through an effects module, and it's being sequenced by this controller here. So I just hit play. Another voice is coming from an audio processor that chops the audio into little grains, also called the granular processor, and in this case I just recorded me doing this, snapping my fingers. Another voice is coming from an audio recorder that plays back the audio in reverse, starting at different points of the recording, and plays different segments of the audio. Another voice is coming from what is actually an effects module, but with the right settings it can act as an oscillator. Its amplitude is controlled by an envelope, and it's being processed through another effects module. I have here another voice coming from a so-called semi-modular synthesizer, going through two different filters from Volt 1 and 2, and also through some effects. And as I mentioned before, I'm using VCV Rack together with the hardware. So in VCV I have another voice coming from another Volt module that generates sound, and I control its filter and amplitude with the MIDI controller that I have here.